Let us talk about introduction to dynamics. This text is concerned with analysis of structure subject to dynamic loads. Actually, dynamic analysis in this context means like time varying. Both application of load as well as removal of load necessarily varies with time. The internal stresses and resulting deflections are also time dependent and dynamic in nature. So in real world, no loads that are applied to a structure are truly static because all bodies possessing mass as well as elasticity and that are capable of vibration. Thus, most engineering machine structures experience vibration to some degree, and the design generally requires consideration of oscillatory behavior. There are some examples. Here we can see that both the application of load as well as removal of load, it varies with time. So internal stresses and deflections also varies with time. Output also varies with time. So in real world, no loads that are truly static because all mass is there and elasticity is there. So there are some capable of vibration, but it depends like how much magnitude or significance is there. The effects of vibration are very common in our daily life, like we live on the beating of our hearts, right? That's a planetary motion is also another example of vibration. These motions are called periodic motions because periodic motion means like motion repeats itself regularly after a certain interval of time. So this interval of time is known as the period of the system or motion. So in general, vibration has both good as well as bad effects. In terms of civil engineering, the good effect of vibration is that we can use that for the complex and fresh concrete. And the bad effects of vibrations on the structure are those produced by natural forces such as wind, gust, and earthquakes, and by mechanical forces of bridge. So these are the good examples as well as bad examples. Motion can be called periodic if it repeats itself regularly after a certain interval of time. That interval of time is known as the period of the system or motion. So we have good effect as well as bad effect. Good effect, we can use it for compacting fresh concrete. That's one example of good effect. The bad effects, we can see that waves, winds, currents, earthquakes, all these things are varying with respect to time. So these are the bad effects of vibration. Oscillatory systems can be broadly characterized as linear, non-linear. In general, for linear systems, the principle of superposition is valid. The mathematical techniques are available or well developed. Whatever the techniques available are well developed, and techniques for analysis of nonlinear systems are less well known and difficult to apply since changes in stiffness as well as damping characters occur during nonlinear inelastic responses. So in general, vibration can be classified free vibration, forced vibration. Free vibration means it takes place when the system oscillates under the actions of forces inherent in the system itself, and external forces are absent. In case of free vibration, external forces are absent. The system under free vibration will vibrate at more than one of its natural frequency, which are properties of dynamic system. Vibration that takes place under the excitation of an external force is called a forced vibration. If the frequency of excitation coincides with one of the natural frequencies of the system, the condition resonance occurs, resulting in a large oscillation of structures, which ultimately results in the failure of the structure. So if you see, there are two kind of vibration. One is free vibration as well as forced vibration. Free vibration will vibrate at one or more of its natural frequencies. Natural frequencies are the dynamic properties of the system. Vibration that takes place under the excitation of the external forces is called forced vibration. Under the excitation of external forces is called forced vibration. If the frequency of excitation coincides with one of the natural frequencies of the system, condition of resonance occurs. Resonance means a large oscillations that can occur, which ultimately results in the failure of the structure. Dynamic loads may be classified as deterministic as well as non-deterministic. If the magnitude and point of application of the load and variation of the load with respect to time are already known, then that is called deterministic loads, and the analysis of the system to such loads is defined as deterministic analysis. On the other hand, if the variation of the load with respect to time is not known, loading is referred to as random or stochastic, then the corresponding analysis termed as non-deterministic analysis. Dynamic loads may also be classified as periodic and non-periodic. When a loading repeats itself after a certain time interval, then it is called a periodic loading. A single form of periodic loading is either sine or cosine function, as shown in figure 1.1a. We will show that figure. And vibration induced due to rotating mass is an example of periodic motion. This see the most periodic loads can be represented by summing up sufficient number of harmonic in terms of Fourier analysis. Any loading which does not come under the category of periodic loading is termed as non-periodic. Blast loading, earthquake motions are examples of non-periodic loads. So here we can say that dynamic loads may be classified periodic loads, non-periodic loads, and if it is repeats itself, that's a periodic loading, and if it is not repeating, that's a non-periodic loading. The periodic load example is a simple harmonic motion. A non-periodic loading, we can say examples of blast loading as well as earthquake ground motions. And one more thing is that if the loading is random, if it is not known, it's a variation of load with respect to time is not known, then that's called random as well as stochastic. So if it is, that is a non-deterministic analysis. If it's known, very well defined, then we can say that that's a deterministic analysis. In two aspects, the dynamic problem is different from a static problem. First and most obvious is that time varying load, and the response is also time varying. Both load as well as response is time varying. That's the first obvious difference. This needs analysis over a specific interval of time. So we need to analyze the specific interval of time. Dynamic analysis is complex, completely expensive compared to the static analysis. Other difference between dynamic and static is a major occurrence of inertia forces. When the loading is dynamically applied, the inertia force is occurring. Consider water tank. Subject, we will show it. If load is F is applied at the top, resulting deflection shear force bending moment can be calculated on the basis of static structural analysis principles. On the other hand, if the load is time varying F of t, load is applied at the top of the structure is set to motion or vibration, and they experience accelerations. According to Newton's second law, inertia force is proportional to the acceleration. So inertia force are proportional to the mass, and they develop in the structure that resists these accelerations. So depending on the contribution made by the inertia force to shear and bending moment will determine whether the dynamic analysis is warranted. So depending upon the contribution made by the inertia force, if the inertia force is quite high, it's contributing more to the shear and bending moment, that will determine whether dynamic analysis required warranted or not. So contribution of inertia force, that's very important factor that determines whether dynamic analysis is warranted or not. Contribution of inertia force, and inertia force is coming from the acceleration. So acceleration is, if it is high, then we can get the inertia force also it's high, that major contribution to shear and bending moment. If the acceleration is less, even the mass is huge, then force is very less, inertia force. It does not contribute anything to that one. So inertia force are proportional to the mass as well as the accelerations. So they develop in the structure that this is these accelerations, right? If the time varying load F of t is applied at the top of the structure set to motion, then it will experience accelerations. If the structure is experiencing accelerations, then it will experience inertia force. That if that contributes more to the static as well as shear as well as bending moment, then we need to consider that dynamic analysis required. Here we can see this example of simple harmonic analysis loading, and then here we can see this is a non-periodic loading, and then this is non-periodic but short duration, just 3 seconds, and this also earthquake is also non-periodic for long duration. So we can have this kind of different types of dynamic loads. Here one more example is that here you can see rotating machine. That's an example of harmonic excitation and explosion. Like a blast analysis is impulsive excitation, and earthquake is a irregular excitation. So we have three kind of excitations, like harmonic excitation. Harmonic, it's a periodic as well as harmonic. This is the impulse excitation, short duration, and irregular motion, irregular excitation, somewhat longer duration. So this is an example for the water tank subject to the static load as well as dynamic load. If you see the static load, it moves this way, so we can calculate the certain deflection as well as bending moment shear forces. In case of this F of t force is applied, then it will experience the inertia forces also. If the mass is quite significant and acceleration is also quite significant, then it will contribute, this inertia force also will additionally contribute to the base shear as well as bending moment and deflections. A physical problem based on certain assumption is that idealized into mechanical model. Then that will be by correctly defining the geometry, kinematics, and loading and boundary condition also. The governing differential equations are solved to obtain the dynamic responses, so the results are interpreted in a meaningful manner, right? For complex structures, it may be necessary to refine the analysis by considering a more detailed mechanical model. In mechanical model, infinite degrees of freedom are converted into finite degrees of freedom, and for each degrees of freedom exhibiting the structure, there exists a natural frequency at which the structure vibrates in a particular mode of vibration. So for each degrees of freedom, there is one natural frequency. A mechanical model can also be characterized as continuous or discrete. Consider the figure in the chimney, that is a real structure that manifests the distributed mass stiffness curves along with the height. But the continuous model is difficult to make it over. And mathematical continuous model incorporates the distributed mass, distributed stiffness to arrive at the response of the system. The displacement function V is displacement is a function of space and time. On the other hand, we can place a whole mass at the top, the chimney, and can consider single degrees of freedom, in which the entire mass is at the top of the structure, so localized, lumped at the top of the structure that has a constant stiffness K. The independent displacement V of t is a function of time alone. The lumped mass representation is 3 degrees of representation with each localized mass m1, m2, m3 has its own displacements v1, v2, v3. That depends on the time. And practical dynamic as a large computer multiple degrees of freedom is generally accomplished by computer implemented numerical techniques such as finite element method. So here there is one important point is that in case of a single degree of freedom, on the other hand, we can place the whole mass at top of the chimney and can consider single degree of freedom, in which the entire mass at the top of the structure, lumped at the top of the structure, as a constant, right? In that case, independent displacement Vt is function of time alone. But if you see here, the continuous model, that is a function of space and time. So where it is different, the space also it matters, which elevation it is there. But here in this case, it's only with respect to time only it is there. It's not with respect to the location. But in case of 3 degrees of freedom, it with respect to the location of the mass as well as time also it matters. So here space and time matters in multiple degrees of freedom. So this is the different mechanical models of chimney. First is a physical representation, and this A, the B is the continuum method. It's a continuously mass distributed and stiffness also distributed. V of x of t is a function of space as well as time. The displacement is a function of space as well as time. In case of single degrees of freedom discrete method, displacement is a function of time only. In case of 3 degrees of freedom also, it's a function of time only at a different degrees of freedom. Types of vibration. Vibration can occur in a structure by imposing initial conditions, which generally manifest themselves as energy input. If the initial input is imparting velocity to the system, the kinetic energy is produced. If the displacement is imparted to the system, then potential energy is produced. If the structural vibration occurs in the absence of external loads, then it's termed free vibration. And free vibration usually occurs at the fundamental natural frequency. Owing to the damping present in the system, the free vibration eventually dampens out. If the vibration takes place under the excitation of the external force, it is called forced vibration. If the source of vibration is periodic, the resulting vibration may constitute both steady state and transient. Steady state response transpires at the frequency of excitation. The transient response is due to the initial energy stored in the structure. The transient response may also occur if the structure is subject to the blast loads.